Okay, so we do not have time to break. Let's directly move to the next section. Okay, so next section is about superb and some related research. So let me share my screen. So can everyone see my screen? Okay, well, so probably someone type something in the chat room if you can see my screen. Okay. Okay, so I'm going to start the presentation. So in this session, I'm going to introduce the superb project is Speech Processing Universal Performance Benchmark. And I'm Hong Yi Li, and we have the website here. And I'm not the one do this project. We have lots of excellent researchers involved in this project. So due to time limitation, I can only put their photo here. I cannot go through all of them. And the members here come from National Taiwan University, CNU, NIT, Johns Hopkins, and Meta AI, LXT, and Hugging Face. And Phil from LXT is also here, and he's going to introduce LXT a little bit. Okay, so Phil, now the stage is yours. You can introduce LXT.
Yeah, sure. And I'll be very brief here. LXT is an AI data company, and we were approached by the Superb team to help them on a research project. We were very excited to do that, but our contribution is very light compared to the heavy lifting that's been done by everyone else. So we provided suitable data. If you could skip to the next slide. So we were asked to participate. I asked the question why, and Superb said, well, we're looking at ways that we can put you out of business. Can you help? And our answer was yes, why not? So if Superb is successful, then the benchmarking, I think, will show that less data is required, and maybe that will put us out of business, but we don't see that as a reason for not participating. Not a lot of challenges for us, other than when Superb approached us, they were working to a very tight timeline to be able to run the next phase of the research. And I'm pleased to say that we were able to meet their timeline requirements, and we were able to do this very cost effectively. So we were very happy to contribute, but that's as much as I'll say on LXT's part. Other than, we are interested in participating in other research projects if folks would like to be in touch with us. Handing back to you, Hong Yi.
Thank you very much, Phil. LXT is a very good partner. And before I start to talk about what we have done in Superb, let me give you some background. And I believe all of you know that there are lots of self-supervised speech models, and here I just named a few. And usually when people build a self-supervised model, they evaluate how good their model is on ASR, on speech recognition. And usually in the paper, people show that those self-supervised models get very good performance on ASR. However, I want to push this even further. In my point of view, I want self-supervised model like operating system. What do I mean by that? So, operating system can support many different applications. And when a developer wants to develop new application, the developer do not have to do lots of work today. If you want to develop an app on your smartphone, it's not very difficult because the operating system, iOS or Android, already take care of the most difficult job. And you can easily develop new application. You can easily add new functionality on your smartphone. can self-supervised learning serve the role of operating system in speech processing? Can they support a wide variety of downstream tasks? And in the future, if you have a new downstream task with a good self-supervised model, you can just plug and play and easily develop new application. So this is what I want self-supervised speech model to do. And to push this research direction, we have Superb. So in Superb, we not only evaluate self-supervised model on one task, we are going to evaluate self-supervised model on a wide range of different tasks, cover all the aspects of speech. So these are the tasks we have evaluated, we have done, and so the block here, we already have 10 tasks published at Interspeech 2021. And for the dotted box here means a new task, which is going to be appear at ACL 2022. And here we have tasks covering different aspects of speech. So we have tasks about content, tasks about speaker, tasks about paralinguistic, tasks about spoken language understanding, and tasks about speech synthesis. We evaluate self-supervised model on a wide range of different tasks. And here, this is the publication. We do not have time to go through the detail of all the tasks. So if you are interested in what we have done, please check the paper published at Interspeech and will be appear in ACL. And until now, we have two leaderboards. We have one published set leaderboard and one hidden set leaderboard. And the leaderboards will always be open. So whenever you have a new idea of self-supervised model, or whenever you train a new self-supervised model, feel free to submit your model, submit your result to our leaderboard. And below, I'm going to briefly introduce the two leaderboards. So the first one is the public set leaderboard. The data here are open data. So we use the open data so you can get the data yourself, and you train the downstream model yourself. You use the development set to select the hyperparameter yourself. You get the result from the testing set yourself, and you submit the result to public leaderboard, and the public leaderboard will show the performance on the testing sets. And we have 3 different tracks. The first one is constraint. Constraint means for all the downstream model, for all the downstream tasks, we only use one self-supervised model. And the parameters of the self-supervised model is fixed. I know usually for different downstream tasks, sometimes people will fine-tune your model parameter for different tasks, but this is not the case here. The self-supervised model's parameter is always fixed. So this is the constraint case. And another characteristic of the constraint case is the network architecture of downstream model is already predefined by us. And we try to keep the downstream model as simple as possible. For example, in ASR, we only use 2-layer LSTM. In SID, speaker identification, we use linear model. And here I show the downstream model we use on 10 different tasks. We try to keep the downstream model as simple as possible. So, and another thing we do is for the output of the self-supervised model, for the representation extracted from obtained from the self-supervised model, we use a layer-wise weighted sum strategy. And we found that this strategy is very powerful. So for all the different layers, they provide different representation, and we weighted sum the representation, and the downstream model take the weighted sum representation as input. And those weights are jointly learned with the downstream model, jointly learned with the downstream test. So you can consider those weights for the layer as part of the downstream model. And why we care about the constraint case? So we fix the self-supervised model, so use one model across all the tasks. And we limit the capacity of the downstream model. So if in this case, we still achieve good performance on all the different downstream tasks, that means our self-supervised model, the self-supervised model, even without fine-tuning, can extract universal feature. If the self-supervised model can extract universal feature, in the future, if you have a new application, you have a new downstream task, you can just plug and play, use the self-supervised model without any fine-tuning and get the good result. And this sounds too good to be true. Originally, I think constraint case is too constrained, so probably we will not see good result. But surprisingly, the result is pretty good. Some model achieve very good performance on this constraint case. So just check, you can check the leaderboard of Superb to see how good the self-supervised model can achieve in the constraint case. And since the constraint case get very good performance, so now we are focused on the constraint case. We also have less constraint and unconstrained case. Less constraint case means still fix the upstream model, but you decide the downstream model architecture yourself. And for unconstrained case, do whatever you want, so you can fine-tune your self-supervised model. But recently, we are focused on constraint case because it already achieved very good performance. And here I show what the public leaderboard look like. This is the constraint case. And on this leaderboard, you can find that WebLN achieved the best performance at this moment. So we invite the author of WebLN to tell us how they achieved that good performance in this session. And here I'm going to talk about how we compare the performance of different models. Here we have two evaluation metrics, rank and score. And it is not easy to compare different models because we have lots of different tasks and different tasks using different metrics, and just simply average the metrics of different tasks doesn't work. So the team have lots of discussion about how to evaluate the overall performance of a self-supervised model. So we have two measures at this moment. One is super rank. So we consider the ranking of a model in each task, and we average the ranking of a model over all the tasks. The second one is super score. We normalize the metrics of each task. We normalize the metric scores of all the tasks into the same range. Then we average the normalized score over all the tasks. I do not have time to go through the detail here. So if you want to know the detail about how we compute super rank and super score, check our webpage. And I know it's not easy to implement 10 downstream tasks. So let me recommend a toolkit to you. So there's a toolkit called S3PRL, and it supports a large amount of upstream model, and it supports more than 15 downstream tasks. So with S3PRL, it's very easy for you to complete all the different tasks in the super leaderboard. And then let me talk about the hidden leaderboard. So only have the public leaderboard is not sufficient because the data is open. So we do not know whether the model are overfit or not. We do, although self-supervised model get good performance in the downstream task, we do not know how much effort people spend on, well, fine-tuning or tuning all the hyperparameter. We do not know whether the model is fit on the open data or not. So we have the hidden data set, which is not public available. So thanks to LXT, they collect the hidden data set for us. We just give them the spec and they give us the data in a very short period. So for the hidden leaderboard, so thanks to Hugging Face to cooperating with us to build this leaderboard, you only have to submit your self-supervised model. You do not have to worry about the downstream task. You do not have to worry about what the downstream task is. Just give us your self-supervised model, input speech, output representation. Then we train the downstream model and evaluate the models for you. For the detail about the spec of the self-supervised model, you have to submit it. Please check the web page below. And so this is what the hidden set leaderboard look like at this moment. And so to make the long story short, we do not have time to discuss the result. But in general, the ranking on the public set and hidden set leaderboards are very similar. So it looks like the good performance of the self-supervised model is not overfitting. Even on the hidden data set, the participants have no idea what the data set is. Well, the self-supervised model still achieves good performance. And we also noticed that the super score is highly correlated to the number of parameters of the self-supervised model. And it is clear that for the model with more parameter, its super score is usually higher. Some model is very powerful, but it's very large. So we also care about whether the model is green. So we have another evaluation matrix, and this evaluation matrix consider the model parameter. It benefits the models with less parameter. You can check the webpage for more detail about how the scores here is computed. And until now, we only consider the number of parameter. I know that for a green model, number of parameter is not the only factor you have to consider. You also have to consider, for example, memory usage, inference time, streaming or not, etc. They are also important factors, and we will consider them in the future. So this is the final page of my part. Here, this is the QR code for Super web page. And so welcome to visit the web page. And the Superb team plans to propose a challenge special session at SOT 2022. So stay tuned to our webpage. So this is my part. Thank you very much for your attention. Then we have 4 talks later. And after the talks, we will have the QA session. So the next talk is self-supervised representation learning for speech using visual grounding and masked language model. And is the author Jason Penn here? Okay, Jason.
Yes, I'm here.
Yes, you can share your screen and start your presentation.
Okay. All right, can you see my screen?
Yes. Yes.
Okay. Hi, so the title of my presentation is Self-supervised representation learning for speech using visual grounding and masked language modeling. I'm Jason, and my advisor is David Howarth. We're from UT Austin. So in the field of visually grounding speech processing, a typical setting is that in addition to the speech, we also have image as input, and the speech describes the content of the image. And we input these 2 modalities into the model and train the model via some objectives. And then we use the representation learned in the model to do downstream tasks such as speech image retrieval, SR, SD, keyword spotting, et cetera, and more low-level, low resource tasks like segmentation, spoken unit discovery, etc. And the workflow is the following. First, we pre-train the VG model on a speech image data set. And then we take the pre-trained model, freeze it, and test it on downstream tasks. Note that we don't have to freeze it, but it's just in this work, we have it frozen all the time. In terms of the downstream tasks, there are 3 of them. First is speech image retrieval. And for this one, we aim at high accuracy and low latency. Second one, language modeling. And we test our model on 0 speech 2021, which means it's the text-free setting. And last one is Superb, which is just introduce the general speech self-supervised learning benchmark. All right. So first, I need to talk a little bit about FastVGS, which our model FastVGS Plus is built upon. This work is going to be presented in ICASP this year. It has conceptually, it's very simple, has an image encoder, audio encoder, cross-model encoder. It produces 2 similarity scores, one using the output of the dual encoder, one using the cross-model encoder. And the the actual implementation looks like this. So we use for the image branch, we use object detector, we use transformers. For the audio branch, we use a bunch of confnets and transformers. And the cross-model encoder is a cross-attentional transformer. Okay. And for the training, on a high level, we have a bunch of images and speech. Some of them match, some of them don't match. And when we input them, when we input matched image and speech into the model, we want the model to produce big similarity scores. When they are unmatched, we want the model to produce small similarity scores. And we do that by using a contrastive loss to train the model. So FastVGS Plus is really a simple generalization of FastVGS. So this is FastVGS, and this is FastVGS Plus. And if you look at the figure in the bottom, you can notice that there are really three additional components here. And if you're familiar with WakeVec, which I believe a lot of you are, so these components are all from WakeVec. So we're using the output of TRM1, the first transformer block, to first input it to TRM3 to contrast with the quantized input, right? At the same time, we also use the output to do further cross-model matching. And because of this, the loss will be changed from just VG loss to VG plus WakeVec loss. Okay. So here is the result on speech image retrieval on spoken Coco. So the left three models are speech image models, and the right two models are text image models trained on MS Coco. We see that first of all, FastVGS Plus significantly outperforms previous state-of-the-art REST-net, and actually come very close compared to DIME ASR, which is the state-of-the-art text image retrieval on MS Coco. And ASR would mean that we use Google speech recognition to provide the text to the model. And if you look at the numbers, they are really close. All right. The second is the Zero Speech 2021. This is a benchmark that examines speech representations in 4 aspects: phonetic, lexical, syntactic, and semantic. In the interest of time, I'm only going to be talking about syntactic and semantic. So let me briefly introduce the syntactic task. So we want a model that can tell if a sentence is syntactically correct. For example, we have a spoken sentence A, dogs eat meat, B, dogs eat meat. And we expect the model to provide pseudo probabilities P such that PA is bigger than PB. And of course, we are not going to use the image branch or the cross-model branch in the model. We only use the audio branch. And in particular, we use the features here. So what we do is exactly as the benchmark baseline. So we train a K-means model on the FastVGS Plus features, and then we assign each frame a K-means cluster. Then we train a bird from scratch on the quantized speech, and then we use the trained bird to produce sentence span probabilities. The semantic task is that we want to calculate the similarity score of model features of 2 spoken words, then calculate the correlation between the similarity score and human judgment. For example, we have word A, exciting, B, happy, and C, sad. And we expect the similarity score between A and B to be bigger than B and C. And again, we're not using the visual or cross-model branch of the model. And in particular, we use the features here. So what we do is that we min pool the FastVGS Plus features of these words to get a vector for each input word. And then we calculate the similarity of these words by just taking the dot product between the vectors. Okay, here is the result on the semantic task on the dataset. we see that visual grounding really boosts the semantic information. And this is the result on the test set. Our model is competing in the VG track. We see that it achieves the best performance on semantic result and very competitive performance on the syntactic task. Okay, superb. We find that our model performs very well on keyword spotting and intent classification. So on keyword spotting, here we only put the best performing model of WaveTVAC, which is WaveTVAC large and Hubert and WaveLM. We see that our model ranked the second on keyword spotting. And note that our model is trained on 1.k hours of audio plus visual context, while WaveLM is trained on 94k hours of audio. On intent classification, see that our model FastVGS Plus also came very close to WaveLM. However, our model performs not as good on speaker identification and ASR. This is the result on speaker identification. You can see that our model almost achieved half of the accuracy as WaveTVAC, but I'm not unhappy with this because it sort of showed that with visual context, the model is able to get rid of the speaker information in its representation. And on ASR, our model is not as good as WaveTVAC, Hubert, or WaveLM, but still better than 8 other models on the leaderboard. In summary, FastVGS Plus achieves SOTA on image speech retrieval benchmarks and comes very close to the SOTA image text retrieval model. Grounding speech with visual context improves the syntactic and semantic information in speech representations. Visual context can drastically reduce the need for large amounts of audio data for classic speech downstream tasks. That's it. Thank you.
Thanks, Jason, for the presentation. We will have the Q&A session at the end of the session, of this session. Okay, so the next talk is WaveLM, large-scale self-supervised pre-training for full-stack speech processing. I believe you will give the presentation.
Yeah. Can you see my screen and hear
Yes.
my voice? Okay.
Yes. Yes.
Okay, great. Hello, everyone. This is Yu from Microsoft Research Asia, and today I'm very glad to present our work with WaveLM, a large-scale unsupervised pre-training for various speech tasks. In the past 3 years, self-supervised learning is a very hot topic in the research field. It brings a new AI paradigm. That is, we can first leverage huge amount of unlabeled data to do self-supervised pre-training, and then we can get a well-initialized pre-trained model to do the supervised fine-tuning with labeled or even no-labeled data for each task. At the beginning, the self-supervised learning model has been verified very effective on language understanding and generation tasks. And in the past years, for speech area and image area, we can see the promising results for self-supervised learning models on image classification, object detection, as well as speech recognition. And it has been verified the self-supervised learning model is an effective way to leverage unlabeled data, and it can show excellent results on limited results task. The focus of previous speech pre-trained model is mainly on the content-related task. It shows very good results on the speech recognition task and the speech translation task. While for WaveLM model, the target is we want to propose a model for full-stack speech processing. We want to handle the content task, denoising task, as well as the speaker task. I think the motivation of WaveLM is well aligned with the motivation of the super benchmark. And then the WaveONM model can be seen as a combination of a better algorithm and large data set, as well as a relatively large models. Regarding the algorithm view, the core idea behind the WaveONM is mask speech prediction and denoising. Given a raw wave, we first tokenize the wave into discrete tokens as what Hoover does. Then we can generate a noisy speech by mixing the noise or speech from other utterance as the input of the transformer model. However, the target is still the discrete tokens of the clean speech. So the difference with the previous work is for WaveONM model, the input is a noisy one, while the target is still the discrete labels of the clean speech. Then we can do both mass speech prediction and denoising tasks. In this way, our goal is we want the model to learn both denoising knowledge and content prediction knowledge at the same time, because the denoising task requires the model to implicitly learn the speaker information or the enhancement information, because we mix some speech or noise from other utterance or from the noise data set. So we hope the model will learn the speaker related information or the noise related signals from the denoising task, and then it can be generalized very well for speech enhancement and speaker recognition task. And here is the ablation study of our algorithm. And because we also change the transformer encoder structure, we also do the ablation study of about the structure change. Actually, for the base size, the structure change is effective. It can provide about 10 relative gain on ASR and phoneme recognition. However, that is just the conclusion for the base size model. When we change the model to the large or even larger parameters, the architecture gains is not as huge as for the base models. We can also see the gain from our denoising task. With the denoising task, we can get better results on the 3 speaker rate tasks, including the identification, verification, and the diarization. Especially for the diarization task, we can see with our denoising task, the diarization error rate decreased about over 20%. So that means the denoising task contributes a lot for the speaker related task. And then let's see the data using in the pre-training. We use about 94K hours data, which is larger than the previous model only used the Libre Lite, about 60K hours data. The 90K hours data consists of gigaspeech, which mostly consists of the European Parliament event recording, and the gigaspeech consisting of the podcast and YouTube data. We can see that is the ablation study from the data part. For base model, if we compare the second row and the third row, we can see if we only increase the data from 960K hours, 960 hours to 60K hours, the gain is very limited. But if we increase the data size to 94K hours, because we put some diverse audios to the pre-training data, the all tasks benefit a lot, especially for the speaker related task. And because we have the better data and we have better algorithm and larger data, currently we achieve the best for the super evaluation. And in addition to the superb evaluation, we also do some fine-tuning for various downstream tasks. The difference is for these 5 tasks, we also update the pre-trained models in the fine-tuning stage. We can see the pre-trained model is a very promising direction for the speech field, because it can achieve very good results on verification, diarization, enhancement, separation, as well as the speech recognition. And at last, we want to do some analysis of the SSL transferability. The first one is we want to compare the different laws. The setting is fair for different models. We can first train on liberal speech and then fine tuning on the Worksylab speaker verification task, and the structure is transformer with ICAPA TDN. ICAPA TDN is a very common used task-specific layer for speaker verification. We can see the table for the result of speaker verification. The second row and the third row are training from scratch models. We can see if we just increase the model size, the ICAPA TDN with the transformer model is even worse than the ICAPA TDN only. And we also test the ASR transfer that we first train on liberal speech and then fine tune on the Worksylab. The ASR pre-training is not that does not have very good transferability, because we can see for self-supervised learning they achieve much lower equal error rate compared to just training an ASR model and then do transfer learning. And then we investigate. Because the Huber model achieves the best performance compared to the Web2Vector and MSAE model, and then we investigate which quantizer shows the best performance for the Huber style laws, the mass speech and prediction. We can see for the SSL model using different quantizer, the different quantizer shows very similar equal error rate for the speaker verification task. The F1 clustering pre-training quantizer is even better on the Worksylab 1 hard test set. So that means the different quantizer shows comparable performance on speaker verifications. So the mask prediction speech loss is the key for a model to have a very good transferability. That is the conclusion for today's talk. The Wave1 is a general speech processing model for various tasks. And the second, we also investigate why a self-supervised learning model has very good transferability. Our experiment result shows the mask speech with pseudo-label prediction is the key for the good generalization ability models, and how to do the pseudo-labeling may not matters for some speaker related tasks. Okay, that is all my presentation. Thank you.
Thanks you for the good presentation. We will have the QA session in the end. Okay, so the next talk is Distill Huber, speech representation learning by layer-wise distillation of hidden universe, given by Heng Rui. Heng Rui, now you can start your presentation.
Okay, thank you, Hong Li. Hello everyone, I'm Heng Rui Zhang from National Taiwan University. Today I'm presenting our work, Distill Huber, speech representation learning by layer-wise distillation of hidden universe. This is a joint work with Xu Wenyang and Hong Yili. So the major contributions of this paper include the first one. We proposed a multitask learning framework to compress pre-trained speech representation models. And it reduced Hubert's size by 75% and speed up by 73%. Also, the distilled model retained Hubert's performance on multiple speech processing tasks. So firstly, why should we compress speech self-supervised learning models? Here, this figure shows speech SSL model sizes and the overall performance across 10 speech processing tasks. The horizontal axis indicates the number of parameters in each SSL model. The vertical axis shows the overall score on the Superb leaderboard. So on the upper right part, the models are powerful in many tasks, but require very large model sizes. So this phenomenon leads to three disadvantages: expensive training, large memory footprint, and slow inference speed, which are the major problems we try to solve. To compress large SSL models, researchers proposed many methods. In natural language processing, DistilBERT and TinyBERT use knowledge distillation to compress pre-trained language models. But we found these methods ineffective for speech models. And in speech processing, Lai et al. Proposed PARP to prune SSL models for speech recognition. But their methods require labeled data for fine-tuning, and we aim to use unlabeled data as other SSL pre-training papers did. So in the next part, I'll introduce the proposed methods. And in this paper, we try to compress the Hubert-based model. It outperforms most other SSL methods on many speech processing tasks. However, it requires 2,000 GPU hours for pre-training and contains 19.5 million parameters, making academia and small corporations difficult to reproduce or applying to products. We use two typical knowledge distillation methods as baselines. The first method is to only distill the last layer's representations. The other is to distill the teacher's hidden layers with students' hidden layers. In order to compress Hubert while preserving its capabilities, we proposed a novel multitask learning framework. It is split into two stages, pre-training and downstream. During pre-training, we freeze the teacher model's parameters to extract hidden representations. Next, we initialize the student network distill Hubert with the teacher's parameters. We add 3 additional prediction heads after the last encoder layer to respectively predicting the 4th, 8th, and 12th hidden layers of Hubert. Distill Hubert is aimed to predict representations similar to the teachers by minimizing the loss functions. After pre-training, the prediction heads are removed and the rest of the model is frozen. The frozen Distill Hubert model can thus offer good representations for multiple downstream tasks. In the last part, I'll show some experiment results to demonstrate the performance of the proposed Distill Hubert framework. In our experiments, we used LibriSpeech 960 hours corpus for pre-training. We implemented our methods with S3PRL. The models are evaluated with 10 downstream tasks in speech processing universal performance benchmark, aka SUPERB. First, we show the overall performance of our proposed method on SUPERB. The teacher model is shown on the upper right part of this plot. So an ideal compressed Hubert model should lie on the upper left part of this plot. As expected, the proposed Distill Hubert lies on the ideal part, simultaneously having a small model and retaining good performance. Next, we show 3 tasks respectively representing semantics, speaker, and content-related problems. Areas for ideal compressed models are shown in red. With the proposed method applied, Distill Hubert offered good performance on these 3 tasks. We also distilled Hubert's last layer with typical methods. However, these conventional knowledge distillation methods failed in some tasks. We also analyzed the model size and inference speed of several models and found Distill Hubert offered significant model size reduction and speed up compared with Hubert. We then analyzed the layer selection method. This plot shows different combinations of layers for Distill Hubert to learn. and the corresponding average accuracy over 3 superb tasks. We found that the proposed layer selection offered balanced representations for different types of tasks. But why the 3 layers? To explain this, we first trained a distill Hubert with 12 prediction heads, each predicting a Hubert's hidden layer. The predicted representations were weighted sum by a set of learnable parameters before fed into the downstream model. We plot 4 downstream tasks weights on the right-hand side to show the importance of each layer to different tasks. We found the top layers are important for content and semantics tasks. Also, the shared representations before prediction heads contain rich information for multiple tasks. This shows that the multi-task learning framework distilled good representations from Hubert. So we chose 3 hidden layers for distill Hubert to learn, expecting it learns balanced representations for different tasks. So in conclusion, we proposed distill Hubert, a novel framework to layer-wise distill knowledge from Hubert. And it retained most of Hubert's performance with significant speedup and model size reduction. And finally, our methods can be easily applied to other speech SSL models, and our code is open sourced on S3PRL. And this is the end of our presentation. More details can be found in the paper. Thanks for listening.
Thanks, Henry. And the last talk is speech representation learning through self-supervised pre-training and multitask fine-tuning. And the last presentation will be given by Yizhen. Yizhen, are you here? Yizhen, you are muted.
Yes, I'm here. Yes.
Okay. You can share your screen and start the presentation. Hello, Yizhen.
Yeah, sorry, I'm sorry, I have to enable the screen sharing, which
So you can not share your screen?
okay. Can you see my screen
Yes,
now?
nice.
All right. Okay, so hi, I'm Yizhen. My professor is Hongyi Li. Today, I'm going to introduce my paper, Speech Representation Learning through Self-Supervised Pre-Training and Multitask Fine-Tuning. First, I want to talk about the motivation. Pre-training is regarded as an effective representation learning approach in deep learning in many areas. The pre-trained model can extract useful representations from inputs, which can then be used in downstream tasks. More specifically, in speech, pre-training approaches through self-supervised learning have achieved huge success. And we pre-train a model and freeze its parameters. Then when we apply it to a downstream task, we use this frozen pre-trained model to extract representations from speech and use the representations to train the downstream head model. We want to investigate other general representation learning approaches where one model can be used to extract representations for a variety of speech processing tasks instead of just one specific task. Besides SSL, there are still other representation learning approaches not systematically studied yet in speech, such as supervised multitask learning. Supervised MTL is to train a shared model on various downstream tasks. When we train a shared model by aggregating gradients from many speech processing tasks, we may obtain a general shared model for speech representation extraction. Superb is a good benchmark for evaluating the performance of one shared model on 10 different speech processing tasks. So in this paper, we use Superb as our testbed as well. It is worth noting that we do not strictly follow the unconstrained rules because we use labels to fine-tune the upstream model in MTL. And there are 10 tasks in Superb. However, because no downstream model training is required in the query by example task, we only perform MTL experiments and compare the results on the other 9 tasks. As for the experimental setup, we use the same Hubert-based model as in the original Superb paper. Because Hubert achieves the overall best performance on Superb, we use a weighted sum of hidden representations of all layers in the Hubert model as the representations for downstream heads. For task-specific head architectures, we simply follow the settings in Superb. In this paper, we study and compare 4 different scenarios, which will be introduced later. And these are the corresponding experimental results. The first column is the scenario. The second column tells what tasks are used in MTL fine-tuning. And the following columns are the performance of each task with their own evaluation metrics. The first scenario is SSL pre-training. In this scenario, the shared model is pre-trained with SSL. For each task, we have a task-specific head model. Then we train each head model respectively as the shared model is frozen. And the second scenario is all task MTL fine-tuning. Similarly, the shared model is pre-trained with SSL. But in this scenario, we further fine-tune the shared model and jointly learn head models with MTL on all tasks. In this way, the shared model can be updated by the gradients of all tasks to fit the respective objectives of each task. Therefore, the representations extracted from the shared model can perform well on the tasks involved in MTL. It serves as a strong baseline for SSL approaches and the following scenarios. So we first look at the first 2 rows of experimental results, where we compare SSL pre-training and all-task MTL scenarios. The performance of the shared model fine-tuned with all-task MTL is better than SSL pre-training in 7 tasks and worse only in slot filling and automatic speaker verification. It indicates that MTL is a strong baseline for SSL pre-training or other representation learning approaches. One thing worth noting is that all tasks except for automatic speaker verification do not suffer from overfitting during training. However, the model is prone to overfit on automatic speaker verification. Because the shared model is jointly trained with the downstream heads of all tasks in MTL, it is hard to select the model checkpoint based on the validation scores of all tasks. In this paper, we simply select the last model checkpoint after 200,000 training steps. It may be a reason for the worst performance of MTL fine-tuning on automatic speaker verification. We leave exploring a better method to select the model checkpoint with MTL in future work. So the third scenario is leave one out MTL fine-tuning. Similarly, we take the SSL pre-trained shared model. Then we further fine-tune the shared model with MTL by jointly training with downstream task-specific heads of all but one task in Superb. Compared to all task MTL scenario, we can observe the influence of removing one task on the learned representations and their performance on the other tasks. So here we compare all task MTL and leave one out MTL scenarios. To make it more clear, we calculate the relative score increase or decrease of leave one out MTL compared to all task MTL and plot 2 relation graphs accordingly. If a task A performs worse or better after removing a task B in MTL, we connect an edge in the improvement or hurt graphs, indicating B can improve or hurt the performance of A. The width of an edge is thicker if the relative change is bigger. From another perspective, The results may provide a different insight in addition to the evaluation of supervised MTL as a representation learning. If we focus on a certain primary task, we may select proper auxiliary tasks to assist the primary task based on these MTL experimental results. For example, if we want to have a better performance on emotion recognition, we can jointly train emotion recognition with all of the other tasks except for speaker identification. And the last scenario is task transfer learning. In this scenario, we take the fine-tuned shared model from the last scenario as the pre-trained shared model. Then we freeze the shared model and only train the downstream head model of the remaining task that is not used in MTL fine-tuning. Compared to SSL pre-training scenario, we can observe the generalizability of the representations learned with MTL on a new task compared to SSL only. On the other hand, in comparison with the representations learned with all task MTL, we can observe how the performance of a task is influenced if this task is not involved in the MTL fine-tuning. So compared to SSL pre-training scenario, all of the tasks except for automatic speech recognition and keyword spotting in task transfer scenario perform worse. It indicates SSL pre-training is still a more generalizable representation learning approach for a new downstream task. On the other hand, compared to all task MTL scenario, all of the tasks except for slot filling perform worse. It indicates whether a task is involved in MTL is crucial to the performance of this task. To obtain better generalizability, it is worth trying to train the shared model with both SSL and MTL at the same time as semi-supervised MTL representation learning in the future. So we leave this exploration in future work. In conclusion, we investigate different training scenarios of supervised MTL as a speech representation learning approach along with SSL pre-training on a benchmark with various speech processing tests. We analyze the generalizability of representations learned with supervised MTL empirically. This paper is only a preliminary study of MTL with various speech processing tests. The performance of MTL is dependent on many factors such as the amount of data, task relationships, noise, and so on. So these factors should be isolated and investigated with more analysis in the future. We also point out some future directions in each experimental section. Thank you for your attention.
Thank you. Thanks, Yizhen. So now is our Q&A. And if the audience have any question, you can type your question in the chat room. And let me first give some question. I have a question to you, Wu. So you mentioned 3 directions to improve the model. You say you have more data, larger model, and a better algorithms. And which one is most effective? And in the future, if you want to further improve Wave LN, what is the strategy you are going to apply?
Yeah, yes, thank you for your question. Yeah, that is a very good question. I think currently, according to our experiment results, the most important factor is the data. Yeah, I think we need a huge amount of data, and the data should be diverse for the pre-training. And according to my evaluation, if the pre-training data match the acoustic background of the text data, then we can get a large improvement on fine-tuning for the downstream task, and also for the model. For the model's size, it's also important, and that is a very interesting phenomenon. That is, maybe we have some good findings for the base size model, but when we increase the model size to large or even to 1 billion model, then the effectiveness of our findings is decreasing. So I think currently my my experience, if we just increase the model size and data size, we can achieve a very good result. But I think there is still some space for innovation, especially for the tiny models and for the small models. I can see the different algorithm may provide different results for the base size or even for some much smaller model size, but for the larger model size, yeah, the result is very similar compared to different models. So I think for some base size and small size models, I may spend some time on investigating which is the best pseudo labels for the Huber spell loss. And currently we found the Huber spell loss is very stable for training models, and it can show consistently better than other models. So we may investigate which is the best quantizer for the Huber cell loss. Yeah.
Thank you very much, Yu. And I also have a question to Jason. So Jason, you mentioned that the image enhanced model is especially good at keyword spotting and intent classification. Can you provide more insight about why this happened to the audience?
Yeah, so I feel like we'll still investigate this property of our model, and our initial finding is that our model sort of can capture word level information, but somehow maybe current character level CTC doesn't reveal what the information that our model can capture. Yeah.
But I have a question. So if your model is good at something like intent classification or keyword spotting, why it is not good at ASR? Because I think ASR and for example, keyword spotting may be highly correlated.
Yeah, because now ASR it's trained on character level CTC, right?
Okay, so you think the model is good at word level stuff, but when it comes to character level, probably it will not work.
Yeah, maybe we have some word level ASR training pipeline. Maybe our model can perform better.
I see. Good point. If we evaluate your model on word level ASR, then we can see whether the hypothesis is true or not. But good insight. Thank you.
Thanks for the question.
So any question from the audience? So if not, probably I have the last question to you. This question is for industry people. You mentioned that small model is also important, but as you know, industry people like to train very large model. But I think compared to NLP model, for example, GPT-3, the speech self-supervised model is relatively smaller. Why don't people try to train a self-supervised model, self-supervised speech model as large as those NLP models? Do you have any idea why this does not happen?
Yeah, I think the maybe one of the reason is for the large model always show their powers on the typical benchmark, and NLP has that benchmark that is a super glue, and we can always see the gains when we enlarging the model size to its extremely large one, and then we can claim we have a certain numbers for the NLP field, but for the Libre speech test set, I mean for the ASR on Libre speech, I think the gain is relatively small compared to the gain we obtained for the super glue test set. So that is one reason, and another reason is for NLP area. I think if we can train a large model, then we can do the teacher-student learning to let the large model to generate the pseudo labels for some data, and then the student model can consume this data to get the better performance on the downstream task. And for the speech area, yes, we can also follow this line, but another line is because the speech. Some speech models often run on device, but for the NLP models, they may run on the service. So I think for the inference time and runtime costs, for the speech models, they are more restricted in the deployment. So maybe we need a smaller and faster pre-trained models for the speech area. Yeah.
Thank you very much for your answer. It's a very good point. So, and when you say we do not have sufficient challenge benchmark corpus, that remind me that probably we need to have super in the future.
Yeah.
Thank you. Oh, okay, so any question from the audience? Okay, if not, let's thank all the speakers again. And this is almost the end of the workshop. We already have the workshop for 10 hours. It's very long, so thank you very much for still being here. I have a very short presentation for the closing.